Okay, I wanted to point out one subtle thing about Lagrangians that I may not have been very clear about in class or brushed over a little bit. And that's the fact that the Lagrangian has to be written in terms of n independent variables. And so a very simple example that illustrates where you can go wrong in this is the puck sliding down a hill. So we have a hill here, and let's say it has a slope m. Actually, so we don't confuse it with mass, we'll call it a slope b. So the rise over 1 ratio is b. If we put an object on here of mass m and let it slide down the hill, normally with the Lagrangian, we'd write the Lagrangian in terms of the distance down the hill as the one variable. But if you naively do this in terms of your regular Cartesian coordinates, so x and y, and let's say this goes through the origin, so it doesn't really matter if we put it at the top of the hill or the bottom. Let's just say it's at the bottom here. So this is the 0, 0 point. Let's change that. Now, if we naively write the Lagrangian for that, we would write the Lagrangian is 1/2 m x dot squared plus y dot squared minus mgy. And then we'd find the equations of motion from that by doing dl dy equals negative mg, dl dy dot equals my dot. Therefore, d by dt, dl dy dot equals my double dot equals negative mg, y double dot equals negative g. And do the same thing for the x. So dl dx is 0. That means the conjugate momentum to x has to be conserved. dl dx dot is 0. Or in other words, dl dx dot is a constant with respect to time. We could call that the momentum in the x direction. And dl dx dot, in this case, is mx dot, which is the momentum we're used to. So mx dot equals px. So we found the acceleration in the y direction is negative g, and the momentum in the x direction is constant. So where did we go wrong? Because this is definitely not right. If you let this ball roll down the hill, it's not going to accelerate in the y direction as fast as a ball that's dropped next to it. So yeah, this ball is going to, or ball or puck, whatever it is, rolling down the hill, is going to move down, and it's not going to accelerate as fast as a ball dropping. It's not going to be gravity. I mean, on an extreme example, if you had a horizontal table, it's flat, it's not going to accelerate at all. If this angle here was, or if the slope was 0, if in this case b is 0. And we also know the x component of the momentum, the mx dot here, is not conserved, because as this ball rolls down the hill, the normal force has an x component that accelerates it in that direction. And yeah, we can see it speeds up as it goes down the hill, and that necessarily means it speeds up in the x direction. So we've done something wrong, and what we've done wrong is we wrote the problem wrong in the first place, and we wrote the Lagrangian in terms of two variables that were not independent. So x and y in this case are not independent, they're related. They're related through the formula y equals, so y equals, in this case, the slope is b, but it's a negative, so y equals negative bx. They're not independent variables. So how do we solve that? Well, normally we'd write the Lagrangian in terms of just the one variable we want, which is how that ball is going down the hill. So maybe the length that's moved down the hill, call that L or U or something like that. But if we did our same process here where we used Lagrangian in terms of the kinetic energy, we would write the Lagrangian is L equals 1/2 m x dot squared. But now y dot is related to x. So y dot is negative bx dot. So we could write y dot squared would be plus b squared x dot squared. And the potential energy, which is mgy, is now mg negative bx. So the whole Lagrangian now becomes Lagrangian is 1/2 m times 1 plus b squared x dot squared plus mgb x. And if we do our Lagrangian dl dx, we get mgb, and dl dx dot equals m1 plus b squared x dot. Therefore, d by dt of dl dx dot equals m times 1 plus b squared x double dot. And from Euler-Lagrange equations, the two are equal, so we have mgb equals m times 1 plus b squared x double dot. Therefore, x double dot equals g times b over 1 plus b squared. Now, does this make more sense? So if the slope is 0, b is 0, that means there's no acceleration in the x direction. If the slope is 1, then we get 1 over 2, so that the acceleration is 1/2. Seems to be right. And if the slope is infinite, you get the acceleration in the x direction is 0 because it's just going to fall straight down. So everything seems to be working out right. So the difference is that we need to remember that x and y do not contribute to the energy independently. Y is basically dependent on x, and so we can't assume that there's a kinetic energy from x and y separately. We have to write their dependency explicitly in the Lagrangian, and then we get the right equations of motion. So yeah, it's a little subtlety of the problem that there are independent variables that define motion. As another example, you could look at a pendulum swinging, and it has some angle theta. And if we wrote the motion in terms of the xy coordinates, so xy, we'd write the Lagrangian is 1/2 m x dot squared plus y dot squared minus mgy. I mean, this Lagrangian looks exactly the same as a free particle, so there's nothing to say that it's a pendulum here. There's nothing showing how x and y are dependent. They are, as far as this Lagrangian is concerned, they're separate degrees of freedom in the system. So if we wanted to do this properly, I mean, the best way to do it, obviously, would be to do it in terms of one variable, this theta value. But if we did want to do it in Cartesian coordinates, we'd have to introduce the equation of constraint, which would say that x squared plus y squared equals L squared. And that would assume that we're measuring everything from this point here. So let's say this point is 0, 0, and this is a length L. And in this diagram here, up is positive for y, and to the right is positive for x. So x squared plus y squared equals L squared. Therefore, y equals square root of L squared minus x squared. Y dot equals, we'd have to do a chain rule here, so we'd get negative x over root L squared minus x squared times x dot. So yeah, you can see it'd be a much more complicated problem. Could we work it out? We can go a few steps further. So Lagrangian now is 1/2 m x dot squared plus y dot squared, which is this expression right above it. So x squared x dot squared over L squared minus x squared minus mg root L squared minus x squared. or the Lagrangian is 1/2 mx dot squared times 1 plus x squared over L squared minus x squared minus mg root L squared minus x squared. So this is getting like really messy because dl dx is very messy. We've got two terms there. I don't feel like working it out. We've got that term and that term that have x in it. Yeah, hopefully that would work to the final answer, which is just much easier to do in the variable that you're the better way to do it is with theta. So the key there is degrees of freedom of the system. If there's n degrees of freedom, you need to use n variables in your Lagrangian. But if it's constrained and there's only n minus 1 degrees of freedom, you have to get rid of one of those variables. So, for example, the ball going down the hill, you have to get rid of y or x. So you could do it in terms of y or x, and you get the same equations, or not the same, but the same physical solution. I hope that clarifies a little subtlety of Lagrangians. Feel free to email me or stop by my office if you have more questions about it.